You know that phone in your pocket, your laptop, your car, pretty much every piece of modern tech you own? Well, inside each one is this tiny, impossibly complex universe. Today, we're going to pull back the curtain on the machine that makes it all possible. A machine so advanced, it honestly feels like it's from the future.
Really, it all comes down to this one question. A modern microchip has tens of billions of transistors. Those are the tiny little on-off switches that do all the thinking. But how in the world do you manufacture something with that many parts, where every single part is almost too small to even imagine?
The scale we're talking about here is, well, it's just about impossible to wrap your head around. The smallest little features on a brand new cutting-edge chip, they measure around 10 nanometers. To put that into perspective for you, that's literally the width of about 45 silicon atoms, all lined up in a neat little row. We're not just building things at this point, we're basically arranging individual atoms. So how on earth do you build a factory that can actually do that?
Well, the answer is a process with a pretty complicated name, but believe it or not, a surprisingly simple idea behind it: photolithography. This is the secret sauce. It's how we can mass produce these impossibly intricate designs by the millions.
Okay, so the simplest way to get what photolithography does is to just think of it as the world's most advanced, most precise photocopier. But instead of copying pages of text, it's copying the blueprint for microchip onto a disk of silicon and shrinking it down millions of times in the process.
Which, of course, leads to the obvious next question, right? A normal photocopier just uses regular old visible light. But to draw lines that are only a few atoms wide, you're going to need a very, very special kind of ink.
And this really gets to the heart of the whole solution. See, using normal light to make a microchip would be like trying to draw a super detailed portrait with a big, thick, permanent marker. The lines are just way too fat. To get the kind of precision you need, you have to use a completely different kind of light: Extreme Ultraviolet, or EUV. It's basically like switching to a pen with an impossibly fine tip.
So how does this impossible photocopier actually work? Well, it all boils down to three core steps. First, you have to create that special EUV light. And you do that by blasting these tiny droplets of tin with two powerful lasers, 50,000 times a second. Second, you shine that light onto a master stencil, which is called a photomask. And third, a super complex system of mirrors grabs that patterned light, shrinks it down, and focuses it onto the silicone wafer, photocopying the design.
Now, describing the process, that's one thing. Actually building a machine to do all of that, that's something else entirely. This isn't just difficult. We're talking about pushing the absolute boundaries of physics and engineering. I mean, just look at some of these challenges. This EUV light is so fragile it gets absorbed by, well, everything, even air. So the entire light path has to happen inside a perfect vacuum. You also can't use any glass lenses, because they just soak up the light too. So you need to use the most flawless mirrors ever created by humans. And all the while, the silicon wafer is being moved around and positioned with an accuracy that's measured in atoms. It's just incredible. This insane level of perfection is all driven by a pretty simple but powerful philosophy from ASML, the Dutch company that builds these machines. Meten is weten, which means to measure is to know. Every single variable, every tiny movement is measured and controlled with mind-bending accuracy. And remember those mirrors? Well, here's the catch. They're not perfect. For every single mirror that the light bounces off of, almost a third of that precious EUV energy is just gone, absorbed into the mirror. And that's exactly why the starting light source has to be so ridiculously powerful, because by the time that light finishes its long journey to the wafer, there's actually very little of the original power left. So, we have this incredible machine, but what is it actually copying? Well, the master document it uses is that photomask we mentioned, and it's an absolute masterpiece in its own right. So, just how much detail are we talking about on one of these stencils? All right, get ready for a pretty wild statistic. If you could translate the lines on just one photomask into text, you could fit all 7 Harry Potter books, the entire English Wikipedia, and every single book in your local library combined. And on that master copy, there can't be a single mistake, not one typo. The machine then takes that perfect pattern and just stamps it over and over and over again onto a 300mm silicon wafer. Now, depending on how big the chip is, you can fit dozens of large ones, like for graphics cards, or almost 1,000 smaller ones, like memory chips, all on one single wafer.
But here's the thing. That's just for one single layer. A modern chip is like a 3D skyscraper of circuits. To build the whole thing up, the machine has to repeat this entire stenciling process about 80 times, carefully stacking one atomic layer on top of another. The whole journey from a blank piece of silicon to finished chips, it takes about 4 months.
So when you put all of this together, you arrive at a pretty staggering conclusion. And it's really not an exaggeration to say that this one type of machine, well, it's the linchpin of our entire digital world. Think about it. Without this machine, there would be no advanced AI, no powerful smartphones in our pockets, no cutting-edge medical research, no global communication network as we know it today. All the technology that really defines our modern lives is built on a foundation that was laid by this impossible machine. And of course, the innovation is not stopping. The next generation of these machines is already being built as we speak, designed to print even finer, even more complex lines, pushing us closer and closer to the absolute physical limits of silicon itself. It's just this relentless march toward the atomic scale, constantly redefining what's possible. And it really makes you wonder, what new worlds will they enable next?